is a security company working on anti-malware, anti-APT products. And I'm also a faculty member at the University of Birmingham in the UK. I do system security. I work on things like vulnerability analysis, botnets. We took over the MedRoot botnet a few years ago, for example. But nowadays, I'm working mostly on malware analysis and detection. A tool that I built that some of you may be familiar with is WebOet for the detection of malicious web pages, for example. So the topic of tonight's talk is malware. So really any kind of malicious code. We're going to see in particular how malware tries to stay sort of behind the radar, not being detected by sophisticated modern analysis environments that have been built by a number of people and companies. We're also going to see how we develop techniques to detect these evasive malware anyways. And I hope that it's going to be a little bit technical, but I hope you will enjoy. Some of the techniques are really cool, I think. All right, so a little bit of background. How has malware changed over the years? There's been a dramatic increasing in the complexity and sophistication of malware. This is something that you may have seen in the news. A few years ago, malware was used mostly for cyber vandalism. In the last 10 years or so, we have seen cyber crime becoming very, very common. Organized criminal groups stealing credit card information, online banking information. What we have seen in the last few years is the emergence of targeted attacks and cyber war and so on. So now, as you see, the complexity, but also the cost of infections with this kind of malware has really shot up. Something that is really interesting from a research point of view is that if you look at this malware and you exclude things like Stuxnet, the really big difference is not so much in the malicious activity. They always do the same things, right? They steal credit card numbers, they steal sensitive information, they steal intellectual property. What really is interesting is how malware tries to evade detection by security companies, security researchers. That's where really if you want, the innovation from the malware authors has gone into. So that's why we say evasion is the new game that we as defenders, we have to fight against. So this is also something that you may be familiar with. There's been a lot of new malware coming up in the years. These are number of new malicious samples that have been produced on a yearly basis. And as you can see, it's really an exponential growth. The numbers for 14 indicate this was taken maybe in April, so a few months ago. Really, this growing trend is continuing. So what does this say? It says that it's really hard to fight malware using traditional techniques. For example, if you rely on signatures, well, you're going to have a very hard time keeping up with the influx of new malware that you see. Another way of looking at this is remembering that, for example, Kaspersky says that they see a new, completely never seen before malicious sample every 2 seconds. Okay, so think of the number of new samples that are coming in and the need that you have to classify them, understand if they are malicious or benign. So that's a big reason behind the fact that nowadays the techniques, the state of the art to detect malware consists of using dynamic analysis techniques. So these are what are commonly called sandboxes. The idea is very simple. You put a binary inside this instrumented environment, you run the piece of binary, and you look at what it does. And depending on the behaviors that you see, you decide if it is malicious or benign. Okay, so very simple idea. You just run the sample, and you see what it does. Very good. Why? Because it's in using this method, you don't care about things like obfuscation, about polymorphism, things that make the life very hard for antiviruses, for example, or for things that are based exclusively on signatures. You can just set up like a farm of virtual machines where the samples is going to be run in this way, and you can semi-easily keep up with the amount of samples that are coming in. So very good technique, very good approach. Also very good because you can, in theory at least, you can handle zero-day threats. So if there is a zero-day an exploit that targets a vulnerability that was not known before, by using these techniques, since you don't have signatures, you're likely to catch it and to realize that there's a new exploit out there. So why do we care about sandboxes? We built our own sandbox at Lastline and previously in as part of our research. A big difference with other sandboxes that maybe you're familiar with is that it's based on full system emulation. What does it mean? It means that basically we are emulating the entire system as we run a sample, and we can look at not only everything that all the actions that the binary is going to do, but before any instruction is executed, we have a chance to look at that action, that instruction, and analyze that and understand more about the sample. And we'll see what it means in just a few slides. All right, so it's very nice. You can basically the instrumentation, the analysis of the behavior of the system, of the sample, is done by from the outside of the system. So in theory, it's very stealthy, very hard for malware to detect that it's running inside a sandbox of this kind. A tool that maybe some of you are familiar with is Anubis, which is an online research sandbox, which is available at that address that you see there, anubis.isaclec.org, which was developed over the years at mainly TU Vienna, University of Vienna, and then at UC, University of California in Santa Barbara. Okay, so this is a slide that tries to show the difference between a traditional sandbox that you see on the left-hand side versus a sandbox that uses full system emulation like the one that we have at Lastline. So a traditional sandbox, what it does is it typically hooks either the system calls or the Windows API calls in order to understand what the malware is doing. And so, for example, if you consider a sample like this, a traditional sandbox understands that it's opening a file and it knows the file name, and maybe it's a sensitive file, maybe the passwords file in the browser. And then you can see that it's reading some bytes of that file, and then it's closing the file. So as an analysis system, you gain a lot of useful information. You know that a sensitive file is being read, but there are some questions that you cannot answer. You don't know what happens between those system calls in the gray boxes that are in there, okay? With full system emulation, instead, the visibility that you have is the one that you see here on the right-hand side. We really see all the instructions before they are executed. We can look at them, we can analyze them, we can do cool sort of data flow analysis to understand more of the behavior of the sample. So for example, after those bytes are read, we can analyze those instructions and figure out what happens to that data. We may learn, for example, that it's being encoded or it's being encrypted before being sent off to some external server, for example. This is an important advantage of having this visibility. Another advantage is that, as we'll see, malware really tries really hard to avoid being detected. Okay, and the way it's done is by adding some checks exactly in those gray areas where traditional sandboxes don't have visibilities. We'll see these checks in detail, but the idea is that there's some instructions there that allows the malware to understand if it is running inside a sandbox rather than an end user's machine. And of course, if the malware realizes that it's running inside a sandbox, it will not do anything malicious, so that the sandbox thinks that it's indeed a benign application, whereas on a real end user's machine, it will do all the malicious activity that it's been programmed for. Okay, so let's look a little bit more at these evasive techniques that modern malware uses. I have to say something very interesting that we are seeing is that traditionally these were used by the more sophisticated, the more targeted malware used in the more sophisticated attacks, but we see very, very, very rapidly these techniques are trickling down to the standard malware, the one that is used in sort of very widespread campaigns. This makes them even more dangerous because now you really need to detect these techniques if you want to analyze even common malware. Okay, so what's the idea? As I said, the malware authors write their code in such a way that it appears to behave in a perfectly benign way on one of these analysis systems in a sandbox, and instead is, of course, very malicious on a regular user's machine. Some of the techniques are the ones that you see here. Malware can detect that the underlying system is virtualized, and this oftentimes is an indication that it is indeed an analysis environment. So for example, it will check if it is running inside VMware, inside QEMU, any of these virtualized environments. Okay, we'll see some of the techniques that it uses to do that. It can exploit differences in the execution of certain instructions on a virtualized system versus the results that they provide on a physical machine. They can check for artifacts in the operating system that indicate that the operating system is actually running inside VMware or QEMU. Something else that we see, another big category of evasive techniques, is malware can detect the presence of a specific analysis environment. It can detect that it's running inside, let's say, Cuckoo, inside Anubis. It has a lot of these checks to check for the presence of files, drivers, or processes that are used in those specific analysis environment. A third sort of class of evasion is malware can try to avoid being analyzed. So what it will do is it will try to, for example, check if there is indeed a human being sort of behind the console. So we'll see some tricks that it uses to determine if there actually is a person running the computer. Or something that it can do is it can leverage the fact that analysis systems typically spend just a few minutes on each sample, because remember, there are so many pieces of malware coming in every day that you need to analyze that you cannot spend more than a few minutes to understand what they do. And so malware exploit this in the way that it doesn't do anything for a couple of minutes. After that time, an analysis system will shut down and will say, the sample is benign, it's not really doing anything interesting. But on an actual user machine, it continues to execute, and only after that time, it will do all the malicious activity. All right, so in a nutshell, the malware authors really try to do, you'll see, in very clever ways sometimes, try to find the differences between analysis systems and actual end users machine. Are these, before we jump in and look at the actual techniques, a question that you may have is how difficult it is to actually implement these techniques and add them to a piece of malware. Well, in certain cases, it's really simple. The thing that you see here is a screenshot of a malware packer. So this is a program that takes an executable, packs it, and makes it harder to detect. As you can see, there are some checkboxes in there that allow to automatically include evasions for specific analysis environments. This one, for example, says anti-Anubis. You want to evade Anubis, just press a checkbox there. This one, a little bit harder to read, but it says anti-sandbox, Norman, CW sandbox, Anubis, a bunch of these publicly available sandboxes. Another one, anti-Anubis, you can see down there. So very, very easy to to include some of these evasive techniques in your standard run-of-the-mill malware. Okay, let's see a little bit more in detail some of these techniques. The first one that I want to talk about is the fact that certain instructions provide different results when they are executed on a physical machine than when they are executed inside a virtualized environment. And the reason for this is that older processors had insufficient support for hardware support for virtualization. So this was first popularized by Rutkowska, who back in a few years ago proposed this that she calls the red pill, which is essentially just one instruction that provides a different result a different number, sets a register to a different value after executing, if it is executing inside VMware or if it is executing on a physical machine. So as a malware author, all you have to do is run these four statements here, check the result, and then perform different actions depending on the result that you see. If the result indicates that you are on VMware, just don't do anything. If it indicates that you are on a real physical machine, just do all the malicious activity, okay? Okay, so things have been improving a little bit over the last few years. Introduction of new architecture that have better support for virtualization. But still there are problems in terms of timing, for example, on virtualized systems and on real physical machines. This idea has been kind of developed even further over the years. This is an academic paper by a bunch of people at University of Milan that automatically discover instructions that have different behaviors on QEMU versus a physical box. So this is obviously a challenge here. One question that you may have is, well, we are going to use more and more virtualized environments, not just for analysis system, but as our regular computing system. So maybe in a few years, malware will not be able to make this assumption that if it is a virtualized system, it implies that it is an analysis system. Okay, so maybe this problem will go away by itself just because virtualized environments are used more commonly. If you remember, second class of evasions was about detecting artifacts of the analysis systems themselves. Some of the techniques that may be used, for example, that we see being used is malware checks for the Windows XP product ID. Over time, they collect all the system IDs, all the licenses IDs, and so on that they find in analysis environments. And so they know that whenever they see that specific ID, they know they're running inside one of these analysis systems. They may check for specific usernames, specific process names, or hard disk names that they know are used by Anubis, Cuckoo, and so on. Other things, a little bit more sort of ingenious if you want, they check for the color of the background pixel. The assumption is if you keep the ugly blue standard background of Windows XP, it's likely going to be an analysis system rather than an actual user's machine. Something else they do is they check that the system is reasonable, has a button, as a mouse, as a keyboard, and so on. So, sort of ingenious things. This is a printout of actual malware code, and these are the x86 instructions that it uses to check if a specific registry key contains substrings that are known to be found in virtualized environments. So you can see there's a VBox, QEMU, VMWA, and so VMware, and so on. So, very, very simple to add, just a few instructions in x86. This is a fairly sort of funny story that goes back to the early years of Anubis. This is taken from one of these underground forums where malware authors exchange techniques and ideas. And so somebody was asking, hey, I need to write a piece of malware that evades the analysis, the online analysis sandboxes. Do you have any suggestion? And somebody pasted this. And if you look, there's one line that says, if the username is Andy, then you detected Anubis. Why was that the case? Well, because the student that at that time was in charge of actually setting up the Anubis images was named Andy. And so, he just was setting up these Windows environments with his username. And so malware authors, after a while, figure, well, if you're running inside a system with user Andy, chances are we are running inside Anubis. So that's something that, of course, we learn. Now we randomize all the usernames, all the registry keys, all the license information, and so on. But that's something that worked back in 2007, I think. All right, so another check that malware does, if you remember, is they check that there actually is a user behind the keyboard. One kind of clever way to do that is to check that the mouse is actually moving. These instructions are taken from a malicious PDF file. So this are the JavaScript instructions that are used to check if the mouse ever moves. If you don't move the mouse during the analysis, the malicious activity are not triggered, and you would conclude that the PDF file is benign. All right, so very simple technique. Something a little bit more sophisticated is the idea of sort of waiting, hoping that if malware is running inside the analysis environment, the analysis system will eventually time out and will not see all the behavior. So a number of different actual techniques here. One is malware can wait until reboot to actually do the malicious activity. They can run only after or before a specific date, so there's a sort of a date-based trigger. Or they can simply sleep for a while. So they can really call the sleep system call with a large number, 10 minutes maybe. Or they can do things a little bit more sophisticated, like executing inside a loop for a very long time, a loop that they know will take a long time to be completed. Okay, so we call this stalling code, because basically the malware is stalling, not doing anything interesting for some time. This is again a printout of a piece of malware that is programmed to run only after a specific date. So very simple kind of code to program in your system if you are a malware author. And this is an example of the procrastination of the stalling loops that are used by malware in the wild. Here, what is interesting is the note that you see there. On a real host, these instructions take only a few milliseconds to execute. On an analysis system like Anubis, they would take 10 hours. Okay, so Anubis is definitely not going to wait for 10 hours, and after a few minutes will say this binary is not doing anything useful. Why does it take a long time? Because it's kind of keeping track of all the system calls that are executed inside that loop, and that takes a very long time. Okay, so these obviously are problems if you, as we do, are working on malware detection, on automated malware detection. How do we go around these techniques? So in a way, how do we build techniques that allow us to evade these evasion mechanisms? Here are some of the techniques that we have come up and that we use in our products. Okay, so let's look at stalling loops. Why stalling loops? Because it's maybe one of the more sophisticated techniques, and one that is really hard to detect unless you have full system emulation that allows you to look at all the instructions. Some of the other techniques that we saw are fairly easy to handle, like checking for a specific username. It's very easy to bypass. You just provide back, when that system call is executed, you just provide back a value that is neutral, does not give away the information that you're running inside your analysis system. But for stalling loops, this is really hard and requires to have a lot of visibility into exactly what the malware is going to execute. So how do we do this? First of all, we detect that the program is not doing any progress. We see that it's always executing in the same code region. The system calls that are executed are really not interesting. And so we have a bunch of heuristics there to tell us, this sample maybe try to evade us by doing stalling loop. When we detect that, we switch into passive mode, which means we disable all the instrumentation that we normally do. We don't keep track of the system calls that are executed, and we basically let the malware execute at full speed. The idea here is that we want to see as much behavior as possible, and we don't care if we miss some activities in there. We just want to make it progress as fast as we can. If that is not enough, we still see that we don't make any progress. We switch to active mode, which is where we actively try to interrupt the loop. So what we want to do here is force the execution of the malware to leave the loop in which it has been stuck for the last analysis time, so that we see more of what it was programmed to do. Okay, let's see how we do this actually. The idea is that we have detected that there is no progress. We stop the execution in a way. We look at the instructions that are going to be executed, and we run a standard program analysis technique, which is called loop detection algorithm, that allows us to identify all the basic blocks, all the groups of instructions that are part of the loop where the program is stuck, okay? So the first thing, when we go in passive mode, we disable instrumentations for all the instructions in the loop. If that is not enough, we need to sort of break out of the loop. How do we do that? Well, we identify the branching node. This is the node where there's the branching condition that says, if the loop is not being taken for 1,000,000 times, stay in the loop. And what we do there is we simply flip the condition of the branching node so that the next time that the program goes there, it will leave the loop and we'll see all the instructions below there that hopefully gives us more information about what the program really wants to do. Okay? So this is the idea. There are quite a bit of sort of subtle points in here. For example, the malware may check after the loop that some condition that was computed inside the loop was actually computed correctly. And we have techniques to handle that. So we do slicing, for example, and we execute all the instructions on that slice very, very quickly. But I'll just kind of ends wave a little bit on the details here, and I'll just go to the sort of the results. So this is an evaluation that we did on tens of thousands of samples from a repository of potentially malicious code. What we found that for a significant chunk of them, 6,000 or more, there was actually they were actually displaying this stalling behavior. Okay, so quite a few of them were actually using these evasive techniques. And then we saw that by applying the techniques that I just discussed, the passive monitoring and then the active breakout, we were able to see significant additional behavior, so actions that we would not otherwise have seen performed by the malware in about 1,500 of these samples. So some of this behavior is really significant. Think of new file activities, new file being created, or even more network activity. So we see connections that we would not have seen without these techniques. So this is pretty cool and allows us to see a lot more behavior and to get a better, classify malicious samples correctly that otherwise we would have thought to be benign. Okay, so this is the how we handle with we actively bypass some of these evasion techniques. The second part of the talk is going to be about detecting evasion. So if you want, this is a sort of a weaker goal. We just want to understand if there is a sample that is trying to evade us. We don't care at this stage about actually being able to bypass it. And we do this in the context of malicious web pages. I don't know if you're familiar with the idea, but there are web pages that, when you visit them, try to exploit vulnerabilities in the browser or plugins that the browser uses, and we have tools to identify these pages and classify them. We have in the web domain exactly the same problem that we have on the binary domains. Web pages that are malicious really try hard to stay under the radar and not display any malicious behavior when they are analyzed by an analyzer, and will, of course, attack a real user. Okay? All right, so how do we handle, what is the idea behind the techniques that we use here? Very simple idea. We say, look, if we see two pages that are very similar, but that are classified differently by our system, so one page is classified as being malicious, the second page is classified as being benign. Something is wrong, right? Because very similar pages, we would expect to see exactly the same classification. So whenever we see these to occur, similar page but different classification, we can, we have techniques to understand why there is this difference, and in some cases, the differences are due to evasion techniques in the malicious web page. So where does this come from? This comes from another tool that we have made publicly available as a research tool. You can find it there at that address, webowet.cs.ucsb.edu. You submit a URL and you get a full report telling you what the page at that URL tries to do when you visit that. And how we do that, we have essentially an emulated browser that goes there and that interprets the page exactly as a browser would do, fetching all the scripts, all the images, all the CSS, and interpreting the JavaScript code. And then looking at the behavior that it sees, it tries to understand if the page is malicious or benign. Okay, so what are some of the techniques that malicious web pages use to bypass a tool like WebOS? Pretty much the same ideas that we saw for binary system. They will try to understand if they're running inside a real browser. So they will try to understand if they are on Internet Explorer or on say a PDF reader. They try to understand if the system is running on top of an actual Windows environment. They try to understand if the user is a real user or not. Okay, this is probably hard to read, but the idea behind this attack is very simple. It's a web page. It lays out a couple of div elements, and then it checks in JavaScript if the offset of the two elements is correct. So it expects that one X position is on the right-hand side of the other because the two elements are supposed to be on the same row. Some analysis systems do not correctly lay out these elements, and so in a way they give away the information that they are not real browsers to the malicious page. This is another cool trick to check that some pages use to check if Outlook Express is installed on the system of the visitor. So they load up a res URL and extract an image from that resource, and they check if the height of that image has a specific number, 59 in this case. If you actually try to look at what it is, it's an image inside the Outlook Express DLL, which of course is supposed to be present only on a real user system rather than on an analysis environment. So how are these checks being used in practice? Well, this is some obfuscated JavaScript code that is used on a malicious web page. This is actually setting up the shell code, doing the heap spraying, all the techniques that malicious malicious web pages use. And this is something that WebOS, for example, would detect pretty easily. The evasion consists of, trying to put a check on top of that. If the check fails, nothing is done. Only if the check is successful, those instructions are executed. This is another technique that is used to evade, in this case specifically WebOS. WebOS pretends to have all kind of vulnerable ActiveX controls and plugins. So whenever a page says, do you have this plugin, it will say, yes, I do. And in this case, the page tries to load a non-existent ActiveX control. So on a real browser, the ActiveX object instruction raises an exception, which is captured, and then the instructions in the catch block are executed. On WebOS, that will say, yes, I do have that ActiveX control, and so the actual exploit is not executed in that case. Okay, so how do we detect that there are these attacks? Again, the idea is, given this page and given this page, they're very similar. If you look at it, there's just one instruction more, one different statement. We would expect that the system classifies them in the same way, either both benign or either both malicious. When that does not happen, there is a difference, and we need to understand if it is an evasion or not. So how do we do this? Well, the idea is we go around, we crawl the web, and we use a system like WebOS to classify all of the pages that we encounter as either benign or malicious. Then we take the pages, we extract all the JavaScript code which is in there. We actually extract the AST, the abstract syntax tree, from the JavaScript, which basically tells us all the sort of components of the JavaScript. There's an if statement, there is a variable name, there's a function invocation. This is information that we have from the AST. Then we compute the similarities between pairs of abstract syntax trees, and we use that to determine if the web pages are similar to each other or not. Okay? So that gives us sort of pairs that tells us the syntax tree at the top is very similar to the syntax tree at the bottom, but their classification is different. One is benign and the other is malicious. And at that point, we have a number of techniques to look at the differences in the JavaScript code. And in some cases, the heuristics that we use allow us to automatically identify differences that are due to evasions. So new evasive checks. Okay, so this is the sort of the idea. Some of the differences are due to things that are less interesting than evasions. But in a good number of cases, we actually have things like the one I was showing before. We have the evasive check at the top, something that is being added completely new on top of the malicious page that we were able to detect. And then there's in red the actual malicious code. All right, so even here, a little bit of a few numbers on the evaluation that we did of the system. We look at 6 million pages. From here, we extract 20 million scripts. There can be more scripts per page, of course, and 186,000 malicious scripts. And then we did this comparison to identify any new evasive techniques that we were not aware of. And if you look, we found that there are 155 groups of ASTs that for which there are similar but have different categorization, and that automatically the difference is attributed to the presence of evasions. So we see about 150 different evasion techniques that are used in the wild to evade automatically, to evade automated analysis systems like WebOS. Okay, so this pretty much concludes my talk. Just to sum up, evasion is one of the key challenges in malware analysis nowadays. We saw that in both binaries and on web pages. It's a big challenge that if you're working on sort of defensive systems, you need to address and have good solutions for. We look at a number of different types of evasions, some of the techniques that malware uses to understand if it's running on an analysis system or not. Some of these have been known for a number of years. Others are more sort of ingenious, more clever, and are becoming more and more sophisticated. We saw a couple of techniques that we use for bypassing these. Some of the techniques are pretty sophisticated. They use a combination of static and dynamic analysis. They're really cool and allow us to really see more of what a piece of binary, what a web page is doing, and to classify these pages and binaries correctly. All right, so that's pretty much all I have. If there are any questions, I'll be happy to take them. We have more information on the lastline.com website. There are white papers when you can read in details everything about the techniques that I just touched on here. But if you have questions.
Une Red Bull, la question?
Thank you for your great presentation.
Thank you.
I have a question about styling code. If a virus use not styling code like doing loops and computation and stuff, instead it uses something like a computation of very big cryptographic functions or something that could be used later in the virus, something that could be totally legit. Is it that easy to detect? So that kind of styling code, which could be absolutely legit in various software.
So let me ask you, the idea is there is a stalling loop, but inside the loop there is a computation that is legitimate and could be checked later on. Is that a question?
Yeah,
okay,
that's a question.
Yeah, so that's kind of where I skipped a little bit some of the details. But so we have an example here. Suppose that the example that we consider is, of course, malware authors know that we can do things like this, and so they always try to find ways around that. So one way that we actually see in malware being used is inside the loop. They do some computation. For example, they may have a counter that counts how many times the loop has actually been taken. And outside of the loop, what they do is they check if that counter variable has this specific value because they know that's the number of times the loop should have been taken. Now, if we do our trick, we leave the loop well before that number has been computed. And so at that point, the malware could kind of detect that we are doing something strange and could still detect us, right? So what we do in this case is we actually keep track of all the variables that are written to, actually the registers, that are written to inside the loop from where we escape. And we leave the loop, as I described before, but before executing further instructions, what we do is we check inside if outside of the loop, there's any variable that depends, any register, whose value depends on values computed inside of the loop. If that's the case, we take this backward slice. So we look at all the instructions that influence the value of, in this case, this counter, okay? And we just execute them at native speed without doing any instrumentation, without doing any check. And so at the end of that, we have recomputed the correct specific value that check is checking for, and we can bypass even that check. So it becomes more complicated, of course, but we can do that.
What kind of action do you detect as nasty? How do you differentiate between a correct behavior and something that the user don't want?
So there again, what actions we?
You said that, for example, if the binary changes the background image, will it be considered as a normal behavior or nasty behavior?
Oh, okay. No. So that was just an example of something that a binary would do to try to understand if it is on an analysis system on a real machine. So they check the color of the background. If it is the standard Windows color, they would say, I'm inside an analysis system. So for handling those things, we have a different technique that we call the multipath exploration. I'll just give you an idea. So you arrive at a certain program point where there is this check. If background color is blue, exit. Otherwise, do all these things. Okay, so when we get there, we can detect that there is these two completely different behaviors, exit or do a lot of stuff. And so what we can do is we can explore both paths in the program automatically. So in one case, background color is blue, we terminate immediately, not interesting. In the other case, we actually see all the other instructions and we may see in there all the malicious behavior. So of course you cannot do these multipath explorations for all the program points. It would take too much time, there are too many paths in the program. But we have heuristics to understand if a check is interesting or is potentially interesting or not. So we can, if you check for things that are in the environment, are you looking for the specific version of Windows and you have very different behaviors depending on the result of that check, that is something that we could identify as worthy of exploring in doing this multipath exploration. So we have techniques to handle those cases as well. Right, thank you.
Thank you.